We live in a world where everything seems to operate by clear rules. A light switch has only two states, on or off, while a ripe apple falling from a tree will inevitably drop to the ground. But if you shrink the world down to the size of the smallest particles of matter, the particles of electrons, photons, or even atoms, those familiar laws begin to falter. In the fantastical world of quantum physics, the strange phenomenon known as quantum superposition has appeared. Challenges all our intuitive understanding of reality. Superposition is not just a dry scientific concept. It is the key that unlocks the door to a world where particles can exist in multiple states simultaneously. Reality only becomes clear when it is observed. To understand the phenomenon of quantum superposition, we must first explore the quantum world, where the classical laws of physics no longer hold true. Daily life unfolds in a fairly predictable way. The car is running on the road with a clearly defined position and speed. When flipping a coin, it will land on heads or tails. But when delving deep into the microscopic world of tiny material particles, the fundamental components that make up all things render the world wondrous and full of mystery. At the quantum level, particles such as electrons or photons do not behave in conventional ways, like little balls that we can easily imagine. Instead, their state is represented by a mathematical concept called the wave function. This wave function cannot precisely determine the position or state of a particle. Instead, it provides a range of probabilities representing possible outcomes, where a particle can exist at a definite position, possess specific energy, or have particular properties. Imagine the wave function as a musical piece encompassing all possible notes that could be played. But only when you play the piece, that is, when observing the particle, does a specific note appear. Before being observed, the particle does not exist in any definite state. It exists in a fantastical mixture of every imaginable state. This is the fundamental nature of quantum superposition. A particle can exist in multiple different states simultaneously until a measurement forces it to settle into a specific state. This concept sounds unbelievable, even absurd. How can something exist in two different states at the same time? But this is not fiction. It has been verified through a series of real-world experiments. The double-slit experiment is the clearest demonstration of the strangeness of the quantum world. Imagine a gun firing electrons toward a screen with two narrow slits. Behind the white screen is a display that records the positions where the electrons enter the state. If you imagine electrons as tiny bullet-like particles, you would assume they fly through one of the two slits and create two separate bright streaks on the screen, each corresponding to a slit. But reality is different. When no one is observing, the electrons create an interference pattern with alternating bright and dark bands, like ripples spreading far when two stones fall into the lake's surface. This phenomenon demonstrates that electrons are not merely particles but also possess wave-like properties. More importantly, this suggests that each electron appears to simultaneously pass through both slits, interfering with itself. But the strangeness doesn't stop there. When you place a measuring device to determine which slit the electron passes through, the interference pattern disappears, and instead you only see two separate bright streaks, as if the electron had chosen to pass through just one slit. This experiment clearly demonstrates the phenomenon of quantum superposition. Before being measured, the electron exists in a superposition state, allowing it to pass through both slits simultaneously. But upon closer observation, the superposition state collapses, and the electron is forced to choose a definite path. This phenomenon occurs not only with electrons but also holds true for photons, atoms, and even larger molecules. The phenomenon of quantum superposition may be an abstract concept, but a famous thought experiment helped popularize it to the public: Schrödinger's cat. Proposed by Austrian physicist Erwin Schrödinger in 1935. This experiment is not intended to explain the phenomenon of superposition, but rather to highlight its peculiarity when applied in the macroscopic world. Imagine a sealed box containing a cat, a vial of poison, a Geiger counter, and a radioactive atom with a 50% chance of decaying within 1 hour. If the nucleus decays, the detector will trigger the mechanism to break the gas vial, causing the cat to die. Conversely, if the nucleus does not decay, the cat will remain alive. According to classical physics, the nucleus exists in only one of two states: decayed or not decayed. Therefore, the cat in the experiment can only be either alive or dead. However, in the quantum world, the nucleus exists in a superposition state, both decayed and not decayed until an observation is made. Since the fate of the cat depends on the nuclear state, it is also considered to be in a superposition, both alive and dead at the same time. Of course, no one actually locks a cat in a box for an experiment. This is merely a metaphor to illustrate that quantum superposition, a perfectly natural phenomenon in the microscopic world, becomes puzzling when applied to large objects like a cat. Schrödinger wanted to emphasize that there are still aspects not fully explained about how the quantum world transitions into the observable macroscopic world. The core of Schrödinger's cat paradox lies in the question: what causes the quantum superposition state to collapse? In this thought experiment, when you open the box and observe the cat, that act forces the system to settle into a definite state, either alive or dead. But in reality, this process is far more complex. In quantum physics, measurement plays a crucial role. When measuring a particle, such as determining its position or momentum, the wave function collapses, and the particle transitions from a superposition state to a specific, well-defined state. But what exactly counts as a measurement, and why does it hold such immense power? Scientists are still debating this issue. Some proponents of the Copenhagen interpretation argue that the measurement process is a special phenomenon that collapses the wave function. Proponents of the multiverse theory argue that every possibility occurs, but in different parallel universes. According to the many worlds interpretation, the Schrödinger's cat scenario splits into two parallel universes, one where the cat survives and another where it has died. Whatever explanation may be correct, quantum superposition remains a fundamental feature of the quantum world. This very characteristic is unlocking new potential applications in technology, particularly in the field of quantum computing. If quantum superposition is a strange phenomenon at the microscopic scale, it is also a highly promising tool in the field of technology. One of the most fascinating applications of quantum superposition is quantum computing, a field that is completely transforming how we process information. To understand the importance of quantum superposition in quantum computing, one must first start with classical computers. In conventional computers, information is encoded in the form of bits and can only exist in one of two states: 0 or 1. With 3 bits, you can represent 8 different states: 000, 001, 010, 011, 100, 101, 110, 111. The computer can only process one state at a time. Now, let's move on to explore quantum computers, where information is encoded through qubits, also known as quantum bits. Unlike classical bits, a qubit, quantum bit, can exist in the state of 0, the state of 1, or a superposition of both. This means that with just 3 qubits, a quantum computer can simultaneously represent all 8 possible states, rather than processing each state one by one. This capability delivers superior computational power. The more qubits there are, the more exponentially the number of states a quantum computer can process increases. For example, with just 3 qubits, quantum bits, we can represent more states than the total number of particles of matter in the observable universe. This does not mean quantum computers will completely replace conventional computers, but they can solve problems that classical computers would take millions of years to process. The phenomenon of quantum entanglement doesn't only occur in laboratories with 2 computers. Some scientists believe it may play a crucial role in the large-scale workings of the universe. For example, the theory of quantum events in black holes suggests that information can exist in a superposition state when crossing the event horizon, thereby raising questions about how information is preserved in the universe. Moreover, the phenomenon of overlapping cultivation may be closely linked to the origins of the universe's formation.